Thank you. Right. Okay, we're moving swiftly on. Our next speaker is Alex Ilgayev. Alex is a senior security researcher at SciCode, and we're going to be talking about GitHub Actions. So, Alex, if you want to share your screen, we'll get.
Yeah, share my screen. Yeah.
Hopefully your screen will work.
Yeah. Can you see it, right?
The floor is yours.
Yeah, thanks for introducing me, Matt. Today's topic will be GitHub Actions security landscape. I'm Alex from SciCode, and I'll present you our latest unique research of GitHub Actions internals, including how we discover and disclose some critical vulnerabilities in several popular open source projects that were using GitHub Actions. So let's start with the agenda. If we'll explore in this talk the security landscape of GitHub Actions, and first we'll learn what is GitHub Actions and why is it really a powerful build system. Then we'll learn what kind of misconfigurations it can have. We'll focus on the code injection as the main scenario of the exploit. Then we'll understand what could be the consequences by exploring the GitHub Actions internals. And finally, we'll explore some of the possible mitigations to stop such attacks. So as I previously said, I'm Alex Ilgayev. I'm a senior security researcher at SciCode. Previously, I was investigating malware threats and checkpoint research. I love anything that relates to security and hacking, so don't hesitate to reach out to me through Twitter. So let's talk a bit about GitHub. For most of its history, GitHub was all about storing source code. In 2018, they announced that they're going in a different but related direction by launching GitHub Actions, which is a CI/CD platform allowing GitHub developers to automate development workflows easily. Since then, GitHub Actions has become extremely popular, mainly due to its rich marketplace, containing more than 12,000 actions and free hosted runners for public repositories. By now, GitHub has over 73 million developers and more than 200 million repositories. Before we go deeper into the misconfigurations we found, let's first understand the possible usages of GitHub Actions. The most popular use case would be probably building your code into a container and uploading to your chosen registry. Could be Docker Hub, JFrog, ECR, GCR, and many, many more. Other possible usages could be creating scheduled tasks to scan vulnerabilities in your repository. It could be running tests or static analysis for a pull request. It could be automatic labeling for issues based on some predefined logic. It could be sending issues to ticket handling system and much, much more. So what is GitHub Actions workflow looks like? So basically, it is a YAML file that contains a name, a triggered event, and jobs. The triggered event in this case is a push event. This means that for every new push to the repository, for every commit, this event will be triggered. And the job in this example contains a single step that just echoes hello world. If we put this workflow file into the path of .github/workflows path in GitHub, and that's it. GitHub Action Service will trigger this workflow whenever we push a new code to the repository. Simple as that. To understand the vulnerabilities, we need first to understand some core mechanics of GitHub Actions. The entity that runs the job is called GitHub Runner, and it is actually an open source project maintained by GitHub. This runner fetches the job from GitHub Action Service and executes them. This runner could be run either on a GitHub hosted machine or which is the more popular solution, or on a self-hosted machine. If a GitHub hosted machine is used, it is also run as an ephemeral environment. This means that each job will run on completely clean VM isolated machine, and once the job is over, the environment will be deleted. In addition, For each job, GitHub creates a temporary token, which can be used to access a GitHub API for various tasks. Such tasks could be updating issues, comments, pull requests, codes, and more. So let's understand this GitHub token and why it is used here. The standard method to access GitHub API is via personal access token. This token contains the same permissions as the user who issued it. This token has two main drawbacks. It can be quite permissive because it isn't limited to specific repositories, and it is usually active for a long duration, which is problematic if it leaks. To overcome using these tokens, GitHub came up with an idea to create a temporary token called GitHub token on each invocation. This token receives default write permissions for most of the events, but it has several limitations. This token scope is for the repository on which the actions are executed, and this token is valid during the action executed period or 24 hours at most. It uses default parameters for many actions, for example, the checkout action. And forked pull requests for public repositories will receive at most read permissions for this GitHub token. Another core mechanic of GitHub Actions is secrets. Using secrets is an integral part of creating meaningful GitHub Actions workflows. When you store secrets in GitHub, they are well encrypted, and whenever an action is requesting one of the secrets, it is decrypted and sent as part of the running command. Examples of such secrets could be cloud tokens, such as AWS, GCP, Azure Access tokens. It could be artifact registry tokens, such as Docker Hub, and more. GitHub separates secrets into three layers of exposure: organization, repository, and repository environment. The first one is secrets defined in an organization. These secrets are exposed to all the repositories, to all the workflows in all the repositories in that organization. In addition, you could also define for each secret, it could be limited to specific repositories. The second exposure level is on the repository level, which means that it will be exposed to all the actions in that repository. And the third one is secretly defined in the repository environment, which we'll talk later in the mitigation part. Now that we learned what GitHub Actions and why is it a powerful CI/CD system, let's understand what code injection is. We created a sample workflow that does the following. This workflow will be triggered whenever a new issue is created, a new issue on GitHub. And it contains one job that's called issue check and single step, and we'll run this bash script. This script checks that if that issue title contains the word bug in the issue, it will trigger a GitHub API request and update that issue with the label bug. This workflow could be used to, for example, to triage issues easily. So in this workflow, we can see this curly brackets, double curly brackets. This is another mechanism that allows workflow developers to use additional information from the triggered event. In this example, we have several such usages. We have this usage for the issue title. We have the usage of the secret of GitHub token. We're using the GitHub token, which we described previously. And we have the issue URL, which we are using to invoke the appropriate API call. So at first sight, this workflow looks innocent, but actually a malicious title could alter this bash script and run a control code. For example, if we send this title for that workflow, this title actually insert the code to the runner and managed to execute this code. It managed to execute this figlet, which prints this pretty psycho text. Because we managed to execute code and on the runner. So is it a bug or a feature? You may think this is a bug, but it is actually mentioned on GitHub documentation. It says that when you create workflows, you should always consider whether your code might execute untrusted input from the attacker. Well, but are all the project owners or maintainers aware of this? Let's check it out. GitHub released a new web tool called GitHub Code Search, which is still in its preview phase. You're welcome to sign up and try it out. So naturally, we ran a few queries using that tool, and we were shocked by the amount of results we found. We looked for suspicious patterns, such as the run command and usage of untrusted input inside that run command, and find many results vulnerable for these bugs. Not every vulnerability is exploitable, and we met a similar situation. Many repositories that contain such injection issues had conditional statements before the vulnerable command, which denied the potential attack. While it reduced the attack surface, we still suggest to such repositories to remove the vulnerable command because these conditional statements could be removed in the future. So we can say it loud that we found an extremely widespread issue. We identified dozens of repositories that share these vulnerabilities in their GitHub Actions workflow. For each repository, we reported it to the maintainers and they fixed it immediately. Out of these dozens of repositories, you can observe the most popular ones. This list contains the following products: Liquibase, which is a popular tool to deploy database schema changes; Dynamo, which is a visual programming tool that Autodesk sponsors; Fauna, which is a transactional database; Wire, which is an open source communication platform; Astro, which is a static site builder, and much, much more. Liquibase on its own claims that its product has been downloaded 75 million times. So we can safely say that when we sum up the users of all these tools, we could reach millions of users. The consequences of such build compromise are quite disastrous. The first major impact is exposing secrets of the vulnerable workflow. Such secrets could be cloud tokens and additional sensitive assets. The second major impact is the ability of the attacker to commit malicious code into the repository. This can cause a critical supply chain incident, as an attacker can introduce backdoors deployed to end users or organization environments. A much smaller risk would be the malicious actor ability to run botnets or crypto miners using the runner infrastructure. So to demonstrate the ability of the attacker to expose secrets, we created an intentionally vulnerable workflow, which will follow us in the example. This workflow will be triggered whenever a new issue is created, similar as previously. It will contain a single job. First, it will contain an environment variable, GitHub token, that will receive the value of the GitHub token. Soon we'll see why we defined it. And contains a single job that's called vuln job and 3 steps. The first steps would be a checkout command, which basically does git clone to the repository to the runner environment. Then it will print the issue title and the issue description. And finally, it will call a GitHub API and update this issue with a new label that this will be new issue. In this process, it will use another secret that's called bot token. So as we showed previously, this run step is vulnerable to code injection. We are not sanitizing the title, the issue title and the issue body. This means that an attacker could compromise the build workflow in this exact step. What could be the consequences of such attack? First, an attacker could get the GitHub token and use it for malicious purposes, and it could get the bot token and also use it for malicious purposes. So we should try to understand how an attacker could do that for both past and future steps that have been used in this action. To achieve that, we created a small setup to test the runner internals. Instead of repeating the process of tweaking the injection and inspecting the results, we wanted to create a reverse shell to ease the exploration. For that, we used the popular tool ngrok. If you're not familiar with it, it allows you to tunnel traffic, whether HTTP or TCP, to a personal computer, even when it's behind the NAT or firewall. So we run the following steps. First, we set up an ngrok on TCP and on port 10,000, which is a chosen local port. Then we received from ngrok cloud the endpoint which we'll use later in the remote script. We run netcat on port 10,000 to listen for the reverse shell. And finally, we could send the malicious script to finalize the reverse shell. So when we send this specific issue title for the specific endpoint we received from the ngrok, we will get our reverse shell almost immediately. After we got this, we started scanning the machine and do some reconnaissance there. We won't overload you with all the details. You're welcome to check the full technical blog for that. But we show some of their main findings in the next part. So let's go back to our previous example. The first method would be getting secrets through environment variables. Because we defined the GitHub token through environment variable, an attacker could simply enumerate all the variables and receive that easily. You can observe the code the attacker could execute to fetch the token. This is pretty simple. The second method attacker could apply for stealing the token is through the checkout step. We explained the checkout command is basically a git clone to the repository and creates a local instance of your code. Behind the scenes, it sends the GitHub token as a default parameter to external action. In addition, whenever we clone a repository using credentials, the Git utility creates a .git/config file containing the credential used to clone that repository. So if that checkout step was used as an attacker, we can fetch that git/config file to get authorization and pipe it through base64 decoding. And we get our GitHub token again. The third method is a bit more complex. During our reconnaissance, we understood that each run command, we have two run commands, each run command before it's been executed, it's also saved as a shell file in the runner environment. So because our attacker has got code execution at this point, it's not seeing the second run command yet, so it sees only this one. So when we going into runner temp directory, which contains this shell file, we have a single shell file that contains the same script as we see in the YAML file, but instead of these placeholders, we have the real values that GitHub Action service inserted. So potentially, if we'll manage to get, this shell file contains secrets in it, so we, as an attacker, will manage to get this if we manage to get the script. The only issue that we don't have the second script yet because we managed to execute only on the first one. The possible solution, simple solution, will be to put some persistent script on the runner and wait when the second script will be written to the disk, to that folder, and when it happens, we can fetch it immediately. So our steps would be creating some server that records all post requests, creating some scripts that record modified shell script in that directory, and send them to some designated server. We pack that script in some Docker container to ease the deployment and run it in this attach mode. This will be the running command. We soon see how it works in a demo. These were the simple methods attacker could apply. Sophisticated attackers could apply a more advanced method. For example, inspecting the memory of the runner worker process or trying to extract some secrets from there. Could be monitoring the created processes or monitoring the network traffic and etc. So let's start with the demos. For the first demo, we'll show how we managed to exfiltrate the secrets in 2 steps. In the first step, we'll exfiltrate the GitHub token, which is quite simple. And the second step, we exfiltrate the bot token, which comes as after we put the persistent script. So let's see the demo. First, we set up the server. Then this is our demo repository. We're sending the malicious issue title. This title contains several commands. As explained, it will exfiltrate it in 2 steps. The first one will be sending the GitHub token to our server, as we can see now. And the second step, we put some Docker container that will monitor that whenever the new file will be written, it will be sent. You could see that on the second step, we received the entire script, as we've seen in the example, together with the secrets we wanted to fetch. So for the second demo, we will commit code to the repository. For that, we created some simple another bash script that receives the file that we want to commit and the path. And it does some Git configurations, very simple. It fetches the file and just Git commit and Git push it. It's quite simple, nothing fancy here. On the runner part, we're going to fetch this script, which on the left side, give it the right permissions and just run it. So let's see that in demo. You can see our repository contains 1 folder and a file. We're creating a new issue. This issue has several steps, as we previously showed. First, it's fetching the script. Then it gives it the right permissions. And then it runs the script together with its input. The first one will be the file that we want to commit. And second will be the path of that file. So now that we check the repository, we can see that it has an additional file that we committed. Okay. It has an additional file that we just managed to commit. In addition, you could see the commit message. This is the innocent commit message which we created, and the maintainer name which we managed to forge. Pretty cool, right? So after we show the possible consequences of build pipeline compromise, let's see how can we mitigate it. The first one will be to avoid run steps. For example, instead of issuing a curl request to GitHub API to update the issue with specific label, we can use an external action, the code labeler, in this example, that does exactly the same. It contains the parameter for the label we want to update. Even if this issue title contains some code, it won't be executed because it's sanitized as an input parameter. The second mitigation, which is the most effective in this method, will be to sanitizing the input. For example, instead of using the issue title and the body inside the run script, we could extract it and define it as an intermediate environment variable, like in this example, and use that variable inside the run script. So same as previously, even if this title or description will contain code, it won't be executed because it's treated as a text. Another effective method for post-exploitation would be to limit token permissions. Inside our YAML file, inside the workflow file, we could add a permission tag, which will indicate the permissions that the GitHub token will receive. Because in our example, we use the GitHub token only to clone the code and to update the issue, we don't need more than these permissions for the GitHub token. This is an effective method for any kind of exploitation, not only this one. So even if the attacker has managed to exploit your vulnerable workflow and execute code, he won't be able to do much with lower permissions. Another method will be to require approval for outside collaborators, which is mainly applied for public repositories. GitHub has introduced some mitigations that new collaborators for repositories won't be able to run workflows unless some maintainer will approve them manually, which is this option. This is a quite good mitigation, but it's a more robust one would be to require approval for every commit that outside collaborators make, because this could be bypassed quite easily. And the last mitigation would be to use environments and branch protection. This is quite a new mitigation that happens in a GitHub Enterprise. It allows you to define several environments for your workflows. For example, production, staging, testing. Each such environment contains its specific secrets. And these environments could be protected for branch protection rules. So this is quite an effective method to protect your secrets. So what will be the takeaways from this talk? Sorry. First of all, even when GitHub does most of the work for handling the build pipeline for you and for the security, including ephemeral environment and VM-based isolation, we are showing that it still can be compromised. This is the most important takeaway from this talk. As we saw in GitHub best practices paper, it delegates some of the responsibilities for securing the workflows to the developers. The issue, I'm a developer myself. I know that developers make mistakes, so this should be handled carefully. The consequences of build pipeline compromise can be quite disastrous and could expose sensitive secrets and cause potential supply chain attacks. And last one, GitHub gives you the tools for securing the build, such as limiting permissions and secrets, sanitizing input variables, and more. We highly advise you to use them. So that's it. Thank you very much for listening. Thank you for DevSecOn for hosting me here. You're welcome to check the full technical details in our blog, in Cycode blog. And if you have any questions, I'm welcome to answer.
Thank you, Alex. That was super interesting. I've got a question. I mean, have you seen any or heard of any examples of these kind of attacks happening in the wild?
Personally, I haven't, but supply chain attacks happens in the wild all the time. And this is just some specific potential supply chain attack. And we didn't hear it, but it doesn't matter that it didn't happen. We just want to prevent it from happening.
Yeah, I mean, I suppose it's, you know, obviously having access to tools like GitHub has been fantastically productive in lots of ways, hasn't it? You know, that people no longer have to kind of run all this infrastructure themselves, but, you know, it definitely does open up the possibilities for attacks. And I think, you know, I mean, as more and more tools start to become parts of these sort of
it develops very quickly. I mean, this attack landscape will increase over the years. I can assure that.
Yeah, I mean, you can see there's already a move to push editors into cloud-based platforms, isn't there? You know, so you start to think about what the possibilities are for being able to attack your code right in the editor is also worrying. Right. Well, I think that's all the questions we had time for. So thank you, Alex. Hopefully you'll stick around for the rest of the conference.
Thank you very much. Thank you for hosting.
Absolute pleasure. Thank you for contributing.